I'm just uploading the subtraction flag gate logic from last time to Moodle, so this way you guys have a reference too. And this tool turns out to be pretty handy for this class. I really like it. The recorder should be on at this point. Yep, it is on. All right. So a little preview of what we are going to do today. We'll have a really quick review of the flags, and then we're going to move on to jump instructions. So at this point, we have talked about the move instruction, which is nothing more than just copying. Okay, copying from memory to register, copying from register to immediate to register, register to register, and so on and so forth. So it's not very exciting. The add instruction is slightly more exciting because you can add two numbers and then store it back into the second operand, which is also called the destination operand. The subtraction instruction works about the same way. You subtract the first operand from the second one, and then you store the result into the second operand. And then we have the compare instruction, which is kind of like a crippled subtraction instruction, because it goes through the entire motion of doing the subtraction, but it doesn't store the result. But all of these instructions, add, subtract, and compare, they all change the flags. The 4 flags that we are interested in this class are the 0 flag, which means is the result 0. The carry flag, which is also the borrow flag, which is basically saying, okay, in the addition or the subtraction, do we have an extra carry or an extra borrow from the most significant bit? We have the sign flag. The sign flag is easy, okay? It is the most significant bit of the result. And it is useful by, because you can tell whether the result is negative or not if you want to interpret the bit pattern as a signed number, okay? It is useless, completely useless for unsigned numbers. And then the last one is the overflow flag, which is the one that is kind of more complicated. That one basically indicates whether the result or the sign of the result makes any sense or not. So those are the 4 flags that we have talked about so far, and doesn't seem like it wants to do the upload. Let me try it one more time.
Are we recording?
I should be recording. Yep, according to this, it is recording, and according to the command line, it is also going. So that's good. It's good to check because yesterday I thought I was recording, and then it was not. For whatever reason, the program stopped halfway through the class. So I only recorded half a class from yesterday's one of my classes. So we'll go ahead and upload from downloads, text processor, and the name of the file is subtraction or subflags.circ. And we'll see whether it uploads or not. It should. Okay, so we have talked about all of these instructions up to this point, but we haven't really talked about any control structures at this point. So what's up with that? We cannot really do a whole lot of programming or writing any programs that are really useful with only sequential operations like move, subtract, add, and compare. In fact, compare doesn't make any sense at all, because all we're doing is to do the subtraction, but don't even store the result. So what is the whole point? Well, the whole point of comparison is to set the flags so that we will be ready to make decisions based on whether the flags are on or off. Okay, so that's what we were. That's what I'm setting up. That's why I'm setting up the class to talk about the flags, and now we are ready to talk about the jump instructions. The jump instructions, interestingly, are the only instructions that are sensitive, quote unquote sensitive, to whether a number is signed or not. Okay, addition doesn't care. Okay, we go through the same logic whether numbers are signed or unsigned. Subtraction, same way. Okay, whether the numbers are supposed to be interpreted signed or unsigned, we use exactly the same logic gates to compute the subtraction. So who really cares about signed versus unsigned? It's the jump instructions, okay, which is a very big deviation from what you learned in cisp310 or any of the high-level programming languages, okay? Because with any type of high-level languages, the comparison operator is the same whether you're comparing signed or unsigned. Okay, there are no jump instructions or go-to instructions, or you're not supposed to use those instructions. But in assembly language programming, this is where all the interesting stuff happens. Okay, move, add, subtract, and compare. Relatively boring. Okay, the flags are more interesting. This is how the flags are actually used in assembly language programming. This is only one link. Even though it looks just like one link, it is a big topic. In a way, it's a big topic. In a way, it is not a big topic. So it kind of depends on how you want to look at things. So we are now moving on to talk about jump instructions. I will go back to the flags a little bit when we get to the right point of time. But at this point, I'm just going to start to talk about the jump instruction. The jump instruction is nothing more than, well, there are several variants of the jump instruction. We'll go to the first one first. No pun intended. Because the jump instruction is also known as go-to in C and C++ programming. How many people at least know about the go-to statement in C and C++? Okay, so for the most part, you know what it is. You can set a label somewhere within the same function, and then use a go-to, so that the execution will continue exactly at the label. Is that your understanding of the go-to instruction or go-to statement? And in your C, C++ class, your cisp310 in this district, did you get the instructions from your professors not to use the go-to statement? Okay, and the reason why you don't want to use that statement is?
It makes it really hard to debug.
Exactly. Okay, it encourages spaghetti code. Okay, it encourages people to write spaghetti code. And many of you, how many people have actually done development in the real world? Okay, how many lines of code are you dealing with? Like in one single subroutine, what is the largest subroutine that you have dealt with?
Probably a few hundred lines for one.
Okay, that's about the same order of magnitude that I had to deal with, except in the case of mine, it also had a lot of go-tos. Now, it's one thing about the go-to when you're deep inside a conditional statement, inside the loop, inside another conditional statement, inside a switch, inside another loop, to go all the way to the end of a subroutine because, okay, this is an erroneous condition, there's absolutely nothing I can do about it, it's time to get out of the subroutine with a flag, okay? That is not really necessarily the best way of doing things because in C and C++, you have the concept of exceptions, and exceptions are a much better way to handle that kind of stuff. But in regular C programming, that is kind of like, yeah, well, I can see why that label is useful and why you might have a go-to go straight to the end of the entire subroutine to get out, okay? Return an error code, get out, and say, okay, nothing I can do about this. This is a really, really bad situation. Except in the code that I had to deal with, there are go-tos from deep inside the control structure into deep inside another control structure, which is really bad. Okay, going into a then branch of a conditional statement that is inside a switch statement, that is really bad because that makes tracking the execution of the code almost impossible because it is not structured at all. Okay. So that's why we learned not to use the go-to statement in C and C++ or any type of high-level language programming. And that is also the reason why I do not like the use of flowcharts. Okay, how many people know what is a flowchart? Okay, most of you know. And the concept of a flowchart is really bad from my perspective because at any branch, okay, you can always look at a single line in a flowchart that indicates, okay, after this step, we go to this step. It doesn't take much for anyone to say, oh, you know what? I want to make a decision here. Okay, and this goes here, somewhere else. And I will put another diamond here to break that branch and merge it with here. And that is, how spaghetti code can be written because, it's just, oh, I can break this execution line, put a conditional statement here, branch all the way to here, and then continue execution at that point. And flowcharting encourages that type of thinking because it is not structured. It doesn't enforce any type of structures. But enough talking about stuff that you already know. So now we will talk about the first branch instruction, which is called unconditional branch or unconditional jump. In some situations, people also call these instructions transfer instructions because they transfer execution point from one particular place to another place in your program. And an unconditional branch is just unconditional. All it does is to use the this is called the mnemonic JMP, and it requires one single memory operand, which is the destination, which is usually a label. It doesn't have to be a label, but it is usually a label. So a jump instruction is just saying, okay, JMP and then a label name. When you execute a program, it will continue execution at the label. Let's go ahead and write a very simple program to illustrate this concept. It doesn't take much, but it doesn't hurt either to illustrate this concept. So consider this a little warm-up of how to use all the tools that we have here. So we'll go ahead and just say jmp.s .text .global start _start, and the tightest loop I can make is this. Okay, it jumps back to the very same instruction that we started off with. Okay, and that's the jump instruction. Okay, you give it a label and you say continue execution at that label. But what is at that label? The very same instruction that I'm executing. Okay, so this is the tightest loop. When we trace this program using GDB, it will just be executing this line over and over and over and over again. Okay, not very exciting. In fact, you may not even think that the program is executing. You may think that the debugger is broken. Okay, because every time you single step, you end up on the same line. So to illustrate that your program is actually executing, it is kind of handy to insert a no op in between. So this way it will go to the no op instruction, jump, and then back to the no instruction, jump, and so on. Okay. Are there any questions about the expected behavior of this program? Okay, let's go ahead and do it. Let's execute this program, run it in GDB, and see whether it is doing what we think it should be doing. Jump is the program, put a breakpoint on line 3 or line 4 are really the same because they correspond to the same memory location. So we'll put a breakpoint on line 4, run the program, single step, single step, single step, single step, single step, single step. You can see that it's not exactly very exciting. The program just is stuck in an infinite loop, which is probably what you would expect too, okay? Because jump is the same as go to in C and C++. So are there any questions about the jump instruction, the unconditional branch instruction? Go ahead.
Did that jump to start or did it jump to NOP?
It's really kind of the same thing because underscore start is the label of the NOP, the no op instruction.
Okay.
So when we say jump to underscore start, we are really jumping to the no op instruction.
So underscore start points to no op.
Underscore start is the label of the location of the no op instruction.
Okay.
So if you think about the program space as a operation manual, each instruction has a page number, then L1 is a bookmark on the no op page.
Okay.
So whenever you say, oh, continue execution at that blue label is on the page where the no op instruction is.
Okay. Okay. And then, so you could, okay, that makes sense.
Yeah, we can take a look at the program again. When we use this line here, underscore start and then the colon, all it's really doing is putting a bookmark on the page that we are on at that time. And then later on, but that page is blank at this time. And the next line, is going to put an instruction onto that page and then advance to the next page. So that's why underscore start is the label of the no op instruction.
So if you wanted to jump underscore to the actual command jump underscore start, you do start +1.
Not exactly, because +1 is +1 byte. So it all depends on how long the instruction no op is. And
Yeah.
in this case, it just turns out that no op is 1 byte. So that will work as well. But in general, instructions can go from 1 byte to 5 or 6 bytes.
Okay.
So if you know the length of an instruction, yeah, you can add a displacement or offset to it. But if you don't know the length of an instruction, then you really kind of have to use a label for that purpose.
Okay.
So the other way to do this, which is more reliable, is to put a label L1 here, and then you'll change it to jump to L1. Because in this case, L1 is the label of the location of the jump instruction itself, so the jump instruction will jump back to itself.
That makes sense.
All right, very good. Okay, so that's not very exciting, but that's the only jump instruction that is not very exciting. It is necessary. We cannot, well, we can live without an unconditional branch instruction, but it's not a good idea. Now here comes the conditional branch instruction. The conditional branch instructions are very interesting. They're not very interesting in many ways, but when you combine these instructions with other things, they are very useful because this is the beginning, this is the fundamental, elemental type of instruction that allows any type of program to branch, okay? And if you think about in C and C++, give me some type of control structures where you have to be able to go this way sometimes and the other way other times. Give me some examples. If statement, conditional statement. What about the other type of statements? What about a loop, a while loop? Do you think a while loop needs to have a decision point and say, well, sometimes we have to go this way and other times we go the other way? Absolutely, right? Because when you get back to the while statement at the beginning, you evaluate the expression. If the expression is non-zero, you continue to go for another iteration. But if the condition is a 0, you branch out and you continue execution somewhere else. That is a branch as well. So all branches eventually will boil down to conditional branch instructions in assembly. So all the fancy stuff that you do in C and C++, all the loops, all the conditional statements, they boil down to conditional branches at some point. And that's why these instructions are particularly useful. So we have a basic set of instructions. JC and JB are really the same instruction. They're just synonyms of exactly the same instruction. And the instruction really is jump if and only if carry or borrow is set in this case. So you still do the same thing. You put a label right next to it, but we do not branch to that label unless the carry flag is set in this case. Okay. JNC, kind of the same thing, but in this case it is the negated version. So we branch if and only if the carry flag is cleared. Okay. And then we have one for the overflow flag, one for the sign flag, and one for the Z flag. Okay. Well, let's go ahead and play with some of these instructions, okay? Because I do want to illustrate, these instructions and say, oh, okay, so that's how it works. So let's go ahead and write a program that illustrates, let's say, the JC, okay, jump if carry set instruction. Okay. So we'll do a program as simple as possible to illustrate this concept. So we have dot text dot global underscore start, and here we have let's go ahead and write a program to do this. So let's deal with a move byte. We'll do call it 2 into register AL. Okay, so register AL is now initialized to a value of 2. We'll put a label here, L1, and all we're going to do is to subtract 1 from AL and until the carry flag or the borrow flag is set. So we'll do a SUBB, which is subtract byte. We are just subtracting 1 in this case from register AL, and then we have a JC. JNC actually is more appropriate here. JNC to L1. So we are branching. As long as the borrow flag is cleared, we will go back to L1, do another subtraction, and then take a look at the carry flag again. If it is not clear, if it is not set, if the carry flag is cleared, we'll go back to L1 again. And then we have the exit code, the typical exit code here. I'm just putting it here just for completeness sake, because I'm not going to trace it. All right. So if we just look at this code here, let's see what's going to happen. Okay, let's think about what should happen, and then we'll trace the program to see whether that's actually what happens or not. The first time we get to, okay, let me put some line numbers up here so we can talk about the lines. So the first time we get to line 6, AL starts off with a value of 2. we subtract 1, so AL ends up with a value of 1. But more interestingly, is the carry flag cleared or not? If I subtract 1 from 2, will it trigger the carry flag to be set? No? Okay. So that means the JNC instruction, will it branch to L1 or will it just continue with the next instruction?
Branch back down.
It will branch back to L1. Very good. So we're back to L1, which is the label of the subtract byte instruction, SUBV. So we'll subtract another 1 from AL. AL at this point has a value of 1. 1 minus 1 is a 0. Okay? But the question is, will that also trigger the carry flag to be set? Nope. So by the time we get to line 7, branch or jump, if not carry, will branch because the carry flag is cleared. So we will go back to L1. So this time, which is the third time we get to line 6, AL starts with a value of 0 this time. 0 minus 1 is all ones, right? And will the carry flag or borrow flag be set in this case? It will be set. So by the time we get to line 7, branch, if not carry, will not go to L1 anymore. So what is the alternative? Okay, the alternative is never really spelled out here. We only say if the carry flag is not set, we go to L1, but the else corresponding to this conditional type of conditional branch is just continuation. In other words, if the carry flag is cleared, line 7 will just go to line 9 to continue execution. Is that okay? All right. If you want to think of it in kind of more or less, C term, this is what it does. Okay, in C term, this is almost like, if not carry, I'm just using C, uppercase C as the carry flag. If not carry, go to L1. That's kind of, the equivalence in C and C++. Well, okay, fine, semicolon. Okay, which also means, if the carry flag is cleared, it is just continuing with whatever is after it. Is that okay? All right. Well, since I'm doing this, I might as well do this too. It's like AL minus equal 1, semicolon. AL is 2, semicolon. Okay. So now we have quote unquote equivalence, in C and C++ of this assembly language code, which is actually kind of a dangerous thing to do because this is kind of the thing that I have to emphasize is it's just one way for you to bridge what you know about C and C++ programming to assembly language programming. But there are fundamental differences between these type of statements. Okay, so let's go ahead and try out this program and see whether it does what we think it should do. So this is jc.ojc.s and link it, gdb it. All right. So with this one, I'm going to put a breakpoint on line 4, which is the first instruction. So run, now we are on line 4, single step line 4. AL should now have a value of 2, so we'll double check, okay? And AL has a value of 2, very good. Now we are ready to execute line, let's see, we single step line 4 already, so we are now ready to single step line 6. So after we single step line 6, there are actually a few things we want to check. We want to print AL, which is 1, but the big question is the carry flag set or not? Okay, so let's take a look, and this time we have to use an info register, which can be abbreviated to IR, and the register that tells you everything about the flags is called E flags. And E flags, when you say IR E flags, it will give you a hexadecimal number, which is corresponding to the 32 bits of the register called E flag. But at the same time, it will give you, in the square brackets, it will tell you which flags are on within the register. So in this case, the I flag, which is also the interrupt flag, is set, but all the other flags are cleared. So if you do not see CF here, which is the carry flag, it means it is cleared. We also see that the 0 flag is cleared, the overflow flag is cleared, and the sign flag is also cleared. Does that make sense? I mean, if you subtract 1 from 2, then all of the flags will be cleared. Does it make sense?
Yeah.
It makes perfect sense. Now, to model this behavior, what you can also do is to go back to what we have done, last time, and yeah, exactly last time. So we can also use LogicSim and use the one file that I uploaded, earlier today, which is subtractionflags.circ, and you can plug in the same numbers. Okay, subtract 1 from 2, and then you can see how the other flags are affected by this particular operation. So we are talking about, okay, let's see, this is the number being to be subtracted from the first one. So this will be 2, 1, 1, 0, 0, 1, 0, which is 2, and this is 0, 0, 0, 1, which is 1. And you can see the 0 flag is cleared because the output is a 1. You can see the sign flag is cleared because the most significant bit is a 0. The output of the subtractor, the carry out, is a 0 because it did not trigger a borrow in the end. And the overflow flag is also cleared because the sign of the result makes sense. You're subtracting a non-negative number from a non-negative number, ending up with a non-negative number. That can happen, okay? So everything makes sense, so now we have all zeros. So this is just another way for you to kind of visualize and understand how the flags are set or cleared depending on, in this case, the gate logic. So getting back to our program here, so when I single step here, okay, because I'm ready to execute the JNC instruction, where do you think I should go? Back to L1, right? So we single step, and sure enough, we are back to L1 because you can see the line number is now back to line 6, which is another subtraction instruction. So I'm not gonna single step through, everything, but this one I think I will single step. Before the subtract instruction, AL has a value of 0 in this case. We single step, we print AL again. It has a value of -1 in signed interpretation, but you can also say, oh, give me the hexadecimal representation, and it is FF, which means they're all ones. More interestingly, what is E flags? Is the carry flag on? What flag should be on at this point? Okay, let's figure this one out before we single step, before we look at the E flags. So we have 0, -1, okay? But in this case, let's just say we have 4 bits. 0 -1 is, okay, I'm not gonna do it step by step, but the end result is we have 1, 1, 1, 1, which is the result of 0 -1 with an extra borrow flag. So what we should get is the carry flag is a 1, the sign flag is a 1, the 0 flag is a 0 because it is non-zero. Okay, 1, 1, 1, 1 definitely is non-zero. And the overflow flag is also cleared. The overflow flag should also be a 0 because it makes sense. Okay, if you subtract a non-negative amount from a non-negative amount, the result can be negative. Okay, it can go positive or negative. So in this case, we are expecting carry set, sign set, and the other 2 flags cleared. Okay, so let's take a look. And we do IRE flags. And we have a whole bunch of flags set here, but we are only interested in the carry flag. It is set. The sign flag is set. And then the other 2 flags, P and A, we are not going to use it in this class. So we'll just say, okay, some extra stuff is there, but we don't care. Okay. So are there any questions at this point about how we can examine the flags using GDB? Because that can be very handy when you're debugging your programs. Questions? All right. If there are no questions, knowing that the carry flag is set in this case, and this is branch if not carried to L1, when we single step, it should continue with whatever instruction is after it instead of going back to L1. So we'll single step, and sure enough, now we're on line 9, which is the instruction just following the JNC instruction. So we're doing okay so far in terms of the concepts of conditional branch instructions. No? Question? Oh, no question. Okay. Is that right?
Yes.
Okay. Go ahead.
JNC must be an acronym for something.
Jump if not carry.
But what is the N for?
Not.
Jump, not carry?
Yeah.
Okay.
Yeah. JC is jump if carry is set. JNC is jump if carry is not set. All right. So we have just illustrated, how to use, a really basic conditional branch instruction in assembly, just JC versus JNC. Remember earlier I said you don't really need the unconditional branch instruction. Well, the reason why you don't really need it is because you can always say in place of jump to L1, you can always replace it with two instructions, JC L1, JNC L1. So that would catch all the possible cases, right? The carry flag can either be set or cleared. So if it is, if either one will catch it to branch to the location. So the unconditional branch instruction is technically not exactly needed, but it is very handy to have it. All right, so the other ones are about the same. This one only pays attention to the overflow flag. Same thing here, but the negation of it, the sign flag, the negation of that, the Z flag, and the negation of that. So, well, that's all that you really need, okay? And we have some of the other instructions. Now, these ones pay attention to L, which is the combination of the sign flag and the overflow flag. So when we go back to Logic Sim, it is kind of clear what the L flag is. This is the L flag here. The L flag is the exclusive OR of the sign flag and the overflow flag. Now the L flag is needed, or kind of needed, because it is the result of the comparison of signed numbers. If the L flag is set, it means the first number is less than the second number, but interpreted in a signed fashion. So it's kind of handy that way. Because you cannot just look at the sign flag and determine which number is larger. You cannot look at just the overflow flag to determine which number is larger, but the exclusive OR of these two flags will tell you exactly which number is smaller. It will tell you whether the first number is smaller than the second number. Let's try that. In this case, we have 2 and we have 1 here. 2 is less than 1 is false. Now 0010 is always 2. Whether you want to look at the number as signed or unsigned, that is 2, okay? Because the non-negative numbers only have one interpretation, whether it's signed or unsigned. So to make this work, kind of illustrate what we're dealing with here, let's look at -2. This 1110 is the representation of -2 using only 4 bits. 1111 is the representation of -1 when interpreted signed. So in this case, -2 is less than -1, and what happens to the L flag? It's a 1, okay? If I reverse this and make this -1, and this is -2, and you can see the L flag is off, okay? So the L flag is just a handy quote-unquote flag. There's no such thing as an L flag in the processor. Well, that might be one using exactly this logic here. But that's how we can determine whether a signed number is less than another signed number or not. Do we have any questions about this picture and kind of how it relates to the conditional branch instructions? Questions? Okay. So getting back to the slide here, JL means the L flag is set, which basically means the exclusive OR of the sign flag and the overflow flag is a 1. JNL means jump if not less than, which means the exclusive OR of the overflow and the sign flag is off, it is cleared. JG is jump if and only if greater than, and it's kind of a strange one because but what are we talking about? Greater than, less than? Where's the compare instruction? Well, the compare instruction is a separate instruction, and that's typically done before the JL, JG, J whatever instruction. Okay, so let's go take a look at this part here. Write a program to utilize a compare instruction followed by a conditional branch instruction. So we'll go back to the other terminal. Okay. So this one, let's go ahead and look at a compare instruction, and we'll deal with signed compare in this case. So in this case, we'll use let's say JG. Okay, so this is an illustration of how to use JG. All right, so we'll do about the same thing as last time. Global _start _start, and this time we'll deal with signed numbers. And when you deal with signed numbers, you can do something like this. Let's deal with bytes only. That's easier to deal with. So we're going to move byte we can put a -1 into register AL, and we'll use another register. Like I don't really need another register. Let's see. Let's make that -4, and then we have label L1 here. At label L1, we have a compare byte instruction. In other words, I'm looking at both operands as only bytes 8-bit quantities. And this time, I'm comparing immediate, let's say -2 to AL. Okay. Now remember, when you look at an instruction like this, we are subtracting -2 from AL. Okay, not the other way around. Except after the subtraction, we are not going to store the result, but it will set the 4 flags that we have been talking about all this time. Okay. Well, not set, but it will affect the 4 flags that we have been talking about here. And then we use a JG instruction. The JG instruction means, if AL is greater than -2, then it will branch to L1, which is actually opposite to what we want. So we want to make it a -1 here. If AL is greater than, so we want to subtract byte here to make it smaller and smaller. And let's go from 0. So 0 is greater than -2. Go back, subtract 1. Okay, that will work. Okay, so we have a very basic control structure here, and if you are to translate this into C terms, what kind of a loop is this? There are only 2 kinds of loops. Okay. Yes, I know some people classify a for loop as another type, but a for loop is nothing more than a while loop, except we put all the things in different places, right?
It's a do while.
This is a do while, exactly. The branch is after the action. Good job. All right. So if I were to translate this into C and C++, which is always a dangerous proposition, this is kind of the same thing as a do. And then inside the do here, we have your AL. Actually, I want to subtract 1, so subtract just 1 is fine, not subtract -1. That's double negation. So I want to subtract 1 from AL. And this is the part that is kind of interesting, because these 2 lines, compare byte and JG combined, is basically saying while AL is greater than -2, or to make it completely C++ compliant, and I have these all the semicolons. Is that okay? That's kind of what it is. Okay. We are subtracting 1 from AL inside for each iteration, but to determine whether to go back and do it again, I'm comparing AL to -2. If AL is greater than -2, then I go back to L1, which is the beginning of the loop. Are we doing okay so far with this code? Kind of, how it is, what the equivalence of this code in C and C++. Is that okay? All right, so if this is okay, I'm just going to add 1 more here, just so that it is complete. Okay. So AL starts with 0. For each iteration, we subtract 1 from it, and we keep going back as long as AL is greater than -2. So eventually, it will be less than or equal to -2, then we get out. All right, so now let's go ahead and assemble this particular program, link it, and then run it. Now this is the sort of thing that I think is going to be very helpful to study for this class. It's not really just reading the notes or listening to the lecture again. The most beneficial thing that you can do to kind of make sure that you understand all the concepts is to read about the concept from my notes. Okay, like just kind of read it and go like, okay, I think I know how this works. Okay, now how do I confirm that my understanding of how this works is correct? Write a 5-line program, 10-line program. Make it as simple as possible, and you say, if I understand this concept correctly, in this particular program, this is going to happen. Okay, this is the result that I'm expecting, and then you just do it exactly the way I did it. Yep.
Are you able to put another jump below that, say, put it on line 9, if that condition wasn't met, then you can have another jump to L1 if other conditions met? And it would
You
still
can,
compare
yeah,
to
you,
AL.
yep, you can certainly have a sequence of conditional branch instructions.
So it'll still just keep comparing AL, or still keep using
What do you want to put on line 9 in this case?
just any jump. I was just saying, the memory that you have in register AL will just keep getting compared. It doesn't like lose the memory or go to somewhere else. Or
It's not a local variable. Is that what you're trying to say?
yeah, something like that. Never mind, just run it.
Okay.
Just run it, I'll see.
Yeah, you can have any instruction after a conditional branch instruction. The question is, what is it and why do you need it there? Okay. We will talk about certain things where that actually makes sense. Okay. But for the time being, we just kind of focus on this program and see whether it does what we think it would do. So we'll put a breakpoint on line 4, and just run the program. When you run the program, the single step line 4, print AL, it is 0. Okay, not really a surprise here. Single step line 6, print AL again. It should be a -1. Okay, it is -1. Single step through line 7. Now this time there's no result in L1 to show me anything because a compare instruction is a subtraction that does not store the result back into the second operand. So if I were to print AL, it would not have changed at all. It is still -1, even though the subtraction quote unquote happened. But the flags would have changed. Okay, the flags will be affected by the compare instruction. So at this point, I'm going to stop and say, okay, we are subtracting -2 from -1. What should I be expecting in terms of the flags? Which one should be cleared? Which one should be set? So this is a good time to cheat here. Okay, we are subtracting -2 from -1, and these are all the flags. The 0 flag should be cleared. The L flag should be cleared. The overflow flag should be cleared. The sign flag should be cleared, and the carry flag should be cleared as well. Okay, so this is what I'm expecting. We go back to the debugger here. We say IR E flags, and this time, when you use IR info register, you do not put a $ in front of E flags because it's a different type of instruction, and in this case, you have to name the register the way it is without a $ in front of it. So IR E flags, press the enter key, and sure enough, none of those 4 flags is set. Okay, they're all cleared. So that's good because it's meeting all the expectations that I have. So JG, which is jump if the second operand is greater than the first operand, should actually branch in this case. Okay, so when I single step, it should continue to go back to label L1, and sure enough, we went back to line 6. This time after this subtraction, we would have gone from -1 to -2. So single step, print AL, it is now a -2. Now we perform the compare instruction. Subtracting 1110 from 1110 should have all the flags cleared except for the Z flag, right? Because the result would be just 0000, which will set the Z flag, but the borrow flag should be cleared, the sign flag should be cleared, and the overflow flag should be cleared. Okay. So we will double check using 2 different ways. First, we plug it in here. -2 minus -2 is 0, which means they are the same. Overflow flag is cleared. L flag is cleared. Sign flag is cleared. Carry flag is cleared. So when we do an IR E flags, we can see that the Z flag of the 4, the Z flag is the only one that is set, which is good. Okay, that's what we're expecting. Now the question is, when I single step on line 8, will it go to L1? It will not, right? Because the JG means if AL, if and only if AL is greater than -2, we branch to L1. But since they are the same, which is not greater than, we should not branch anymore. So this single step on line 8 should continue execution to the exit code. And sure enough, we are now on line 10, which is a continuation of following the JG instruction. Are we doing okay so far with these instructions? They're not really quite what you would expect here, like in C and C++, where you can just say compare okay, and then use the result of the compare. So in this case, compare is one instruction, which is really just going through the subtraction, going through the motion of subtraction. But the relational part, which is greater than, less than, greater than or equal to, less than or equal to, not equal to, those are controlled by the conditional branch instruction. So a typical comparison expression in C and C++ is actually broken up into two different parts. The compare instruction, which you always need, and a conditional branch instruction after that to say, oh, we just had a compare, but under what relationship of the comparison should I branch to the other label? And it's broken up into two parts. It is also helpful at this point to kind of illustrate how to read a general pattern of compare followed by a conditional branch instruction. So what I'll do is I'll just do a compare instruction first. The width of the comparison is not important in this case, so I'm not going to state the width of the comparison. So I would just use certain symbols here, okay, to represent the first operand, or the first operand here. So we'll just call the first operand B with in square bracket, and then this is operand A in square brackets, which basically means they're just placeholders. Okay, they're not actual things that you can put into an instruction. I'm just referring to component A and component B. And after that, we have a conditional branch instruction. We'll just call this a C. It's not the same thing as a character. Let's not use C because it's too confusing. Let's make it X. Okay. To a label, we'll just call the label L. Okay. So this is a general pattern of a compare instruction followed by a conditional branch instruction. So how do we read something like this as a combination? This is the same thing as, okay, if A, L, B go to, whoops, X is here, L is here. Yep, there we go. Okay. This pair of instructions is equivalent to kind of like this in C and C++. Let's check it out, okay? Let's check out whether this makes sense or not. In our current program, we have compare byte, Okay, so I'm just gonna copy and paste it. Okay. Copy, and then we have the conditional branch instruction here. Paste. Control. Oh. I type Control C when I'm not supposed to. Copy and paste. There we go. All right. So if we are looking at these two instructions, does it fit this pattern? Does it fit this pattern here? A compare instruction followed by a conditional branch instruction. It fits the pattern, right? So once it fits the pattern, what is A here? What is equivalent to the slot labeled A? AL, right? Register AL. What is taking the slot of X, which is the relationship? G, right? Greater than, okay? What is taking up the slot of B? $-2, the immediate operand. And what is taking the label, what is taking up the placeholder of L? In this case, L1. So it means, if and only if AL as a register is greater than the value -2, go to L1. Okay. It takes a while to kind of figure out this pattern. Okay. Even though I tell you, right now, how to read it, just to get used to the zigzagging of reading it takes a little bit of time. But the more you do it, the quicker it will get. The quicker you will get used to it, which is basically saying, if A is blah blah B, go to label L1. Okay. The more you do it, the quicker you get used to it, and the quicker you get used to it, the quicker you can write the next program using control structures. Are we doing okay so far with this stuff here? Okay. So let's take a look at the notes again. So we have JL, JNL, JG, JNG, and then we have JA. Now JA, okay, now here comes the big confusion. What is JA versus JG? One is jump if and only if it is greater than. The other one is jump if and only if it is above. Greater than applies to signed numbers. Above applies to unsigned numbers. Okay, so the easy way to remember this is unsigned numbers are easy as ABC. Because JA, JB, and JC, they all apply to unsigned numbers after a comparison. Unsigned numbers are easy as ABC. So that leaves, L, G, JL, JG, to apply to signed numbers. What about JZ? The numbers or the values are the same. Do you think equal is going to be signed or unsigned? Or it doesn't matter at all? Does not matter, right? After a subtraction, if the Z flag is set, it means whatever you're comparing are the same. Whether it is a signed number or whether it's representing a signed value or not does not matter. Okay, 14 is the same as 14. -2 is the same as -2, so it does not matter which way you interpret 1110 as a 4-bit pattern. Is that making any sense? So the only time whether it's signed or not makes any sense is when you involve greater than or less than. If you just need to know whether they are the same or not, then it doesn't matter. You just look at the Z flag and you're done. Are we doing okay so far with all this stuff here? Okay. So here comes the other part. JL can now be translated to jump if and only if the exclusive OR of the sign flag and the overflow flag is a 1. J and L is kind of saying the opposite, right? Now you can see that J and L is not the same as a JG. The difference is the 0 flag. J and L is saying jump if and only if not less than. Not less than includes two cases: greater than and equal to. Am I making any sense? But JG does not include equal to. So that's why JNL and JG are different. Let's take a look at one of the ones that are kind of difficult, like this one, JG. So do you think, given the other instructions like JS, JO, JNS, JNO, and JZ and JNZ, I can implement JG without using JG? Do you think that's possible? Okay, let me rephrase that question. Let's say we have an architecture that does not give me the JG instruction, but it does give me all of these instructions. Looking at JC, JB, JNC, JNB, these 8 instructions are available along with the unconditional branch instruction, JNP. So if this instruction is not available, can I implement the same effect of JG to L1 only using the unconditional branch instruction and a whole bunch of these other instructions? The answer is yes, okay? But how do we do it? Let's do it as an in-class exercise, okay? So the objective is to implement JG, so I'm going to use a notepad here to do it. So the concept is implement JG to label L1 using only JC, JNC, J. I'm going to just put a bracket here, to simplify all this stuff here. Sign, and then we have the 0. Okay. So only using those 8 instructions, we want to implement, and the jump instruction, the unconditional branch instruction. So only using these 9 instructions can I implement JG to L1. The answer is yes, okay? We can certainly do that with additional labels too. And when you look at the flags, this is the condition where we have to branch to to label L1. For all other cases, we have to continue execution. So let's go ahead and figure out how to do this. Okay, what would be a good starting point? I think we just take care of the Z flag first. Okay, if the Z flag is set, I definitely don't want to go to L1. Is that making any sense? If the Z flag is set, it means the two numbers are equal after the compare. If they are equal, one cannot possibly be greater than the other one. We can just move on. Making any sense? Okay, so we'll go ahead and deal with that first. So the first instruction is just a JZ instruction to a new label that I just call L2. L2 is my continuation point. Okay, whatever the next instruction is at L2. Okay, I'm just creating a new label so that I can continue execution. So if JZ to L2 did not happen, it did not go to label L2, now I can look at the other flag and say, oh, okay, should we continue or not? At this point, I'm really looking at the exclusive OR of the sign flag and the overflow flag, because that combined is telling me whether a number is less than the other number or not. Is that making any sense? Okay, so at this point, it really doesn't matter which one I pick or whether it's negated or not. I just need to pick one, okay? So at this point, I really have 4 choices, and they're all quote-unquote the same. I can use JS, JO, JNS, or JNO. Okay, which one I start with makes no difference whatsoever at this point. I just randomly pick one. Let's say JS, jump if signed. And we'll give it another label. Let's call L3, okay? Now this is the way I write assembly language program. Whenever I use a conditional branch instruction, I will kind of tell, I can tell where the label is supposed to be, like, after the instruction or before the instruction. And what I'll do is I'm going to use comment here and say the sign flag is guaranteed to be a 0 at this point because it did not branch to L3. And then at this point here, I also comment and say at this point the sign flag is guaranteed to be a 1. Okay, because otherwise the conditional branch would not have happened. Are we doing okay so far? This is just a personal, practice thing that I kind of found useful for my own programming practice. Okay, if the sign flag is a 0, how can I make the L flag 0? The L flag, by the way, is just the exclusive OR of the sign flag and the overflow flag. I already know at this point where the blinking cursor is, I already know that the sign flag is cleared. So in order to go to the original label L1, what should I use here? Okay, first of all, which flag should I be paying attention to? The overflow flag, okay? So 0 exclusive OR what is 0? So the question now is, okay, I know the sign flag is a 0 already. This is the overflow flag, and I have an exclusive OR operation here. Oh, much too much X-Men. There we go. Now we have exclusive OR man. Zorman. Which can be a great spoof of X-Men, I think. I'm already thinking about all the possibilities, all the super, binary, geeky mutants, from this series. Okay, so the question is, what should I put here so that the result, which is the L flag, is a 0? Because that's what I want. Okay, I already know they're not equal. The C flag is already cleared at this time. But what should I put here?
0.
A 0, exactly. So we want the overflow flag to also be a 0 to branch to L1, because that's a confirmation that that I'm waiting for. So if I want the overflow flag to be cleared, I can use JNO, jump if overflow is not set, or jump if not overflow. Is that making any sense? But what if the overflow flag is set? Because JNO is conditional, okay? It may happen, it may not happen. If I continue execution, it means that the overflow flag is a 1, because that's the only time I would continue execution and not go to L1. In that case, I should continue execution, so I would use an unconditional branch to L2, which is my continuation point. So that takes care of one side of the branches. Over here, at this point, at label L3, I know that the sign flag has to be set because I came here from JS L3, which is here, right? And that's a confirmation that the sign flag has to be a 1. So now my question is, I know the sign flag is a 1. I don't know what the overflow flag is. I want the L flag to be 0 so that I can go to label L1. So the question is, what should I put here in order for the result to be a 0? 1, exactly. When you look up the exclusive OR table, one exclusive or one is a 0. Okay, so which instruction should I put here? I want the overflow flag to be set, okay? So jump if overflow to L1, which is the place that I want to be if the second number is greater than the first number. But there's always a chance that the overflow flag is cleared because it's a conditional branch instruction. So if the overflow flag is cleared, I can, just say jump to L2, which is not needed, because if I just do nothing after the JO instruction, it will continue execution at L2 anyway. So the branch instruction is really not needed, but it's just put here to be like explicitly clear that we continue execution if the JO instruction did not branch to L1. Are we doing okay so far? Okay. So that's how we write programs in assembly language. I mean, it really is a little bit different from how you write your C and C++ code. How many people had a calculator that is programmable in similar ways? You have branches, but the branches are only like, oh, greater than, you go to a certain place. It's not structured like C and C++. Which calculator is that? Say again?
84.
A TI-84? Does anyone else have a TI-84? Yeah. Okay. So you're already kind of familiar with concepts like these, because it is non-structured. This is definitely not structured programming, but that's the only type of programming you can do in C and C++. But this is also a good time to kind of bring us back to the discussion of CISC versus RISC. In a CISC architecture, which the i386 is, it will give you an instruction like this, the JG instruction. In a RISC architecture, they won't give you an instruction like that. Instead, they will just give you these instructions, which are very basic. They look at only one flag to decide whether to go to the label or not. And then you, as a programmer, okay, sorry about that, you as a programmer will now have to say, oh, I want to implement JG, but since the instruction is not available, I'm going to have to do it this way. I'm pretty sure there's a way to optimize this code and make it shorter, maybe. But that's what you need to do with a RISC architecture. You have to implement kind of more complex logic using your own code because the more complex version of the instruction does not exist. All right, is that okay so far? All right. If that is okay, then we're pretty much all done with this slide here because we just talked about the most complicated one. This is one of the most complicated one. All of the other ones are actually simpler compared to this one. And by the way, in this particular notation, this symbol means what? And, yep, and that is OR. The V symbol is OR, the little TP symbol is actually AND. This is exclusive OR. Okay. All right. In the Intel architecture, they also offer even more complex instructions, which we are not going to use, okay? And since we are already using a lot of time to talk about the computer architecture, what is inside the processor, I'm going to skip this section, which means it cannot be in your exams, okay? So I'm going to skip this section here. We will not talk about J, C, X, Z, and all of the other instructions. The only one that is kind of notable, well, many of these are notable, but I think loop is actually pretty notable. Loop is notable for one reason. It has an implicit operand of CX. Okay, so when you look at the instruction or when you read the instruction, loop to the operand, direct memory operand, which is basically is just a label that you specify where you want to branch to. So loop to the label L1 or L whatever, CX times. So it is actually implicitly using CX as a counter. Okay? This instruction combines the decrement, test, and JCXZ into one single instruction. And that's why we have registered A, B, C, D. It's not really just taking the next letter out of the alphabet and say, oh, let's name the first one A and the second one B and the next one C and the last one D. C means something. Can someone tell me what C means in this case? Counter. Yep, C is actually a counter. And this is an instruction that is dedicated Okay, you cannot use register AX for this purpose, or BX, or DX. This instruction has to use CX as a register for counting. Okay, this is also a typical setup with a CISC architecture where certain registers are special purpose. In other words, certain instructions must use certain registers and not any of the other registers. And this is a remnant feature from the good old days where the x86 was still a 16-bit, or probably even before that, the 8085 processor, which is an 8-bit processor, probably has instructions like these already. And we are not going to use it in this class, okay? So I'm not even going to talk about it in this class. But it is kind of interesting to see how, these instructions are hardwired to use certain registers only. This one we have talked about already, just in a different way. It's the same thing. Let me just kind of go back to my notes here. It's the same thing as this section here, the top part here. That's basically what this section is talking about. How to read a combination of a compare instruction followed by a conditional branch instruction. Same thing. Okay. Are there any questions about all of these instructions so far? Questions? And I believe there is only one example left. Okay, let's go ahead and do this instruction here. Finish this example as a program. Given unsigned numbers, num1 and num2, find the product. And in this case, we're not going to do it the smart way, using the multiply instruction and stuff like that, or using fit shifting and all that good stuff. We're going to do it the dumb way. Okay. In other words, if someone tells me, oh, what is 4 times 5? I will say, well, 4 times 5 is 4 plus 4 plus 4 plus 4 plus 4. Okay, we'll do it the slow way. Okay. So the algorithm to do it the slow way is to allocate one variable to store the product. And I'm given the two numbers. Assuming I can destroy the numbers themselves, I would say if num1, the first number, is greater than 0, I still got something to do. For each iteration, I'm just going to add num2 to product, and I will subtract 1 from num1, go back and see if num1 is still greater than 0, and keep doing this, keep decrementing num1 for each iteration until num1 is 0. Okay, is that making any sense? The slow way to do multiplication. Okay, so let's go ahead and implement this. And let's see, let's go ahead and do it. So I will write the program on one side and let you see the pseudocode on the other side. So we'll just do, let's call this mult, okay, multiplication. So we'll do the same thing here, dot text, dot global underscore start, and I will start with the code right here and say product. Let's pick one register to store the product. Do you want to deal with long numbers or short numbers? Doesn't matter to me. Yeah, let's pick 8-bit numbers. Okay. So we'll just use 8-bit numbers here, and I will just use a register DL for my product. Okay. So DL is product, and now we have a while loop. So whenever you see a while loop in pseudocode, it looks a little bit different than in C, but it's the same thing. It's still a pre-checking loop, which means we need to define a label first because we know that sometimes we have to come back to this point. So we'll define a label L1, and in this case, because it is actually a known control structure, I'm not going to use L1, which is a really generic name for a label. So I would say this is while begin. This is the beginning of a while loop. And what I'm going to do here is, first thing is a compare, and then the second thing is a conditional branch. Now this time I'm going to write, I'll write this part first. Okay, that's the easy part. I'm comparing 0 to register DL. Because you have to put it in an opposite order. Okay, num1 is greater than 0 has to be expressed kind of in an opposite way. The left-hand side of the comparison has to be the second operand. Okay, and the other one goes to the other side. So it's a little bit flipped. The big question here is, what should I do here? Okay. Most people think in the quote-unquote positive logic, which means if the condition is num1 is greater than 0, we want a JA in this case because JG applies to only signed numbers. JA applies to unsigned numbers. Remember, unsigned numbers are easy as ABC. Okay, so JA, which is jump if above, in this case, seems to apply to this case. But what we actually do is to do the opposite. Okay, in this case, we'll say JNA to get out of the loop. So we actually say JNA out of the loop. So I will name the end of the loop while end, and I will define it right away. Okay, so this way I don't forget to define the label, or have to think about, oh, where am I supposed to put that label? This one does not need a semicolon. Okay, so in comments, I'm gonna say if DL is not less than, which is greater than or equal to 0, go to while end. Is that, if you just look at the pseudo C version of this code, does it seem to make sense? Does it seem to make sense for a while loop? I'm looking for the negation of the condition, and if the negation of the condition is true, I get out of the loop. Okay. What should I do inside the loop? Well, I have to add num2 to the product. Okay. Actually, it doesn't make any sense because I'm using the product for comparison. You guys need to. I'm just checking whether you're paying attention or not. It seems like nobody's paying attention except for me. No, I actually used the wrong register. I caught it. Okay, so we have to comment here and say AL is num1, and that will make BL is num2. All right, so if BL is num2, how do I add BL to DL? Because DL is product. Do we have any instruction that can do that? Do addition, store the sum back into one of the two numbers. Just add B, yep. Add byte. So the first operand is not the one that is storing anything, so that would be num2. Num2 is BL in this case, and product, which is the one that is both a part of the addition and the one that is storing the result, is DL. So this will implement product against product plus num2. And the last instruction per iteration is to subtract 1 from num1. We have subtract byte. We are just subtracting 1 from num1, and num1 is AL, so we'll subtract it from AL. So the comment is num1 gets, okay, I'm just getting lazy. And do we need anything here? I need a jump instruction, because in C and C++ and in pseudocode, it is implied. This is structured code. At the end of each iteration of a loop, it is understood that we go back and reevaluate the condition and decide whether we have another iteration or not. But in assembly language programming, there is no such implicit operation of going back to the beginning. So if you intend to go back to the beginning, you have to state so. You have to say, oh, we need to go back to the beginning now to reevaluate the condition. Okay? This is the one thing that a lot of people miss, at least at the beginning of this class, okay, is to miss, oh, this is a loop, and they forgot to go back to the beginning, so it becomes a one-shot thing. All right, so we are now done with this program, which is really great timing, because now we can run the program. We have just enough time to test the program. And somebody's going to say, but AL and BL are not initialized. They're definitely not initialized. We can do it in the debugger, okay? So let's go ahead and test this program. -o is volt.o.s. Volt is the program. Put a breakpoint on line. Yeah, I'll put it on line 8. Okay, well, 5 is fine. Okay, so now we are running the program. Single step. Print DL, it is 0. So I need to put something into AL and BL. So what do you want to do? What kind of multiplication do you want to do? It's 8-bit only, so we can only have a product up to 127. Can't be too fancy. How about 2 and 3? 2 times 3 is 6. Sounds good to you? Okay. So the way you do it is to use the command called set. So you can say set AL to be 2, set ABL to be 3, Okay. Now I'm going to double check. Are we really sure this is going to change the registers? So we can use IR, EAX, IR, EBX. And sure enough, the registers are changed by the instruction called, set in GDB. So now we can run the program. If you think this program is going to work and be brave about it, you can just run all the way through and just put a breakpoint at the exit point. If you are not quite sure how it works, you can just single step through it. Okay, it's only going to go through the loop twice because 2 minus 1 is 1, 1 minus 1 is 0, so it won't go through twice. So let's just go ahead and single step everything. So we single step. This is right after the compare instruction. AL has a value of 2. 2 minus 0 is non-zero, and it is above because it's not below. So if it is non-zero and it's not below, it is above. So if it is above, it should not go to end while. So we single step, and it did go to end while. Uh-oh. If AL minus 0 is 2, 2 is about 0, so it should not branch. Okay, now I need to debug my own program. But the way to debug it is to do IR, E flags, just to look at the flags here. All of the flags are cleared. So JNA it is above, so JNA should not happen. Okay. Let's double check the program. I have 3 minutes to debug this program. Okay. JNA branch to end. Okay, I'm just gonna read the code here. Branch to while end if and only if AL is not above 0.
Exactly what we're supposed to.
Yeah, I went to line 11.
I think the logic is right? Okay, branch to end while end if and only if AL is not above 0. When it is 2, it is above 0. When it is 2, it is above 0. It should not do the branch. The flags are consistent with what I want to, because with this, it should become 0, and the Z flag should be set, and that's why I will go to while end.
So if it runs properly, the next instruction should be the add instruction.
If it runs properly, after the next instruction should be the add instruction. Correct.
Isn't that what it was?
Sorry?
That's not what it was?
It went all the way to this line, I thought. Or did I? Oh, I messed up in the debugger. Okay. Never mind. It's not a brain fart. It's called a super brain fart. Okay, let's do it again. This time we will stop on line 9. Okay, so single step. JNA should not branch, so that means continuation on line 11. Oh, okay. I forgot. I put a breakpoint back into the first line, which is line 5. Run the program again from the beginning because I forgot to change AL and BL. So we have to set AL to 2 again, set BL to 3 again. Continue execution, single step, single step. This is the right thing to do. Right thing to do, go back to the beginning, compare again. This time AL should be 1. And it should not go to end while. And go back to the beginning. This time AL is 0. 0 minus 0 is 0. So it's going to branch, but that's because the Z flag is set. So we will examine IRE flags, and the Z flag is set. So that means I should actually do the branch this time, because if the Z flag is set, it is not above for sure. So we should single step, and it goes to end while. And DL should now have a product, which is 6, and so the program does work. Okay. I was reading my own code and I forgot about, oh, the next line is line 11. I thought line 11 is like after that. All right. So are there any questions about this code? Okay, because the preview is next time we'll talk about structured code. We are done with conditional branches already. So the next time we talk about, we'll talk about control structures. And don't leave just yet, because this is kind of important. There are 2 notes related to control structures. So what you want to do is to read the new one instead of the old one. So we are now going on to topic 5. And topic 5 has 2 control structures. Let me see which one is the more recent one, and that's the one that you should read. This is the more recent one. The first link is the one link that you want to read. Okay. So the first thing we want to do next time is to talk about conditions in general. Okay. There are 2 things to do. One is, if you look at C code, how do you translate the C code into assembly code? That's a structured way to do it. And that's the control structure part. You see a while loop, how do you translate it into assembly code? You see a conditional statement, how do you translate it into assembly code? But the second one, or the more difficult problem, is what if you have conjunction, which is and, disjunction, which is or, and negation somewhere involved in the expression. Okay? We never really talk about that, right? We talk about comparison. But what if you have, a condition that is A is less than B and B is less than C? How do you deal with the conjunction? So that's the part, this part here that deals with the conjunction, disjunction, and negation. So we have some strategies to reduce those operators into assembly instructions. That's it. This entire thing, this entire module will basically turn you into a simple compiler. I'll be able to give you any C code in any control structure, and you'll be able to reduce everything down to assembly code. Okay, so that's the objective of this particular slide, is to deal with control structures. We won't have any abilities to deal with local variables or we can deal with global variables, but not local variables or subroutines. That's kind of a later topic. Okay, and don't forget there's a homework assignment that is due on Thursday. And that's it. I forgot to take roll again.
One day you'll remember. One day you'll remember.
I have to stick it into my notes, like every 5 lines, there's a note here. Okay, remember to take roll.
We're all here.
I'll turn all my material to script facing, so remember the take roll thing is going to be inserted automatically.
There you go. Just pop it on.
Yep. Do not proceed until you take roll.
It won't let you click past.
Yeah, just the header is not a file.
All right. It's kind of a good thing if I can